find a particular solution. If you have a fundamental solution set, you can use this technique, variation of parameters, I'm worthy now. Woohoo. Did I ever show you guys this? That's not what's really fun, though. See. That's a laser pointer. Do you guys have one of these? One of my students got it for me from China. Somebody gave me one of these in the middle of a lecture once. It was like my laser ran out of batteries or something. And I remember that for the rest of the day, I had a green dot burned in my retina. So. All right, so if you were looking at the nth order problem, you don't have 2 parameters, you have n parameters. So you have to differentiate, you just keep differentiating and differentiating. And you always, every time, impose a condition that the terms with just the first derivatives in the parameter are 0. The first one you get is that these terms are 0. And again, it's basically, once you've done n equals 2, you start to understand why you do that. It's because we're looking for an equation, a linear equation, and the derivatives of the parameters that we can solve. And you might recognize that this being 0, well, that's the first row of the Wronskian matrix, y1 through yn. And then this being 0, it's the second row in the Wronskian matrix, and so forth. And that just keeps going. And going, and going. And eventually you get to the n minus 1th derivative, and so altogether you got n minus 1 constraints on these guys, and then when you get to the nth derivative, I think it is, you plug it back into the differential equation, and it's a kind of tedious, long calculation, but after some stuff cancels out, you eventually find that the analog to equation 9 is this. So you have zeros all the way down, you have the force over A naught, and you've got the Wronskian matrix just the same. But here's the difference. Now we've got n equations and n unknowns. How do you solve this for that? Well, you guys like to use Cramer's rule, right? You've done that in circuits? You guys aren't all electrical. You doing it in circuits? Not yet? Well, there's something called Cramer's rule that allows you to solve it. Cramer's rule gives you just a straight up formula for solving for whichever variable you want. It's not very efficient from a linear algebra perspective. We kind of downplay it because Gaussian elimination is so much more efficient. But if you're out for formulas, it's the way to go. The way Cramer's rule works is as follows. If you want to solve this equation, AV equals to B, what you do is you take the coefficient matrix A and you replace the kth column with the inhomogeneous vector, the B. And you call that matrix SK. I call it SK. All right. So SK is it's got all the same coefficients. So here, S1, see what it is? We took the first column in the coefficient matrix and we replaced it with the inhomogeneous term. See that? Everything else is the same. Just the first column has been replaced with this guy. So S2, you leave the first column alone, leave the third column alone, replace the second column with the inhomogeneous term. And then S3 is like that. All right. Then what you do is you calculate the determinant of these SKs. All right. Let me call them. I don't have a good name for them. And and then you calculate the determinant of the coefficient matrix A. And Cramer's rule says this: the solution is just the determinant of SK divided by determinant of A. So you guys see why you like it. It's just a formula. There's no like solving and substituting and logic and anything terribly algorithm. I mean, this is a really simple, but, well, I get, the devil's in the details. These determinants, they're kind of awful, right? That's why it's not really the best method. But it is a simple method to understand. And it's really nice for solving symbolic problems. So you can do Cramer's rule and solve our linear equation on the parameters here. And in so doing, you get the generalized variation of parameters formulas like this. So this is V1 is so you call that the first. These are called sub-Wronskians. So like the first sub-Wronskian, the second sub-Wronskian, the nth sub-Wronskian. So like the kth sub-Wronskian is formed by calculating the Wronskian of all of the functions you're looking at, but removing the kth one. So like the first Wronskian, so if I was to look at the first, so in the n equals 2 case, we're looking at like the Wronskian of y1 and y2, right? So like the first Wronskian or the second Wronskian just has y2, this one just has y1. And there's a sign, plus or minus, that gets wrapped into that. That's where the plus or minus comes from. Oh, wait a minute. I'm wrong. The plus or minus is, well, sorry, it's been a little bit. Oh, here, I defined this by that. It's just what I said. And then, so the expansion, so I put the sign in right here. I have a choice, right? I'm defining this WK. I could either wrap the plus or minus into my WK thing, or I could leave it somewhere else. I left it somewhere else. That's what I was ambivalent about. Anyway, so there is just straight up nth order variation of parameters. Even at n equals 3, you've got to calculate 4 3x3 determinants to do this problem. And then you've got integrals to do. Here's an example. Well, before I get to the example, actually, I would just like to point out that variation of parameters is general. So let's take a second to smell the roses here. Go back to the n equals 1 case, right? You have a naught dy dx plus a1y equals to f. This we solved with the integrating factor method, remember? But you can also solve it by variation of parameters. See, because the Wronskian here is just y1. If you have a single function, the Wronskian's just, the determinant of a 1 by 1 matrix is just the number. And so the sub-Wronskian's just 1. It follows the solution y equals to y1 v1 has v1 equals to the integral of f times the sub-Wronskian, which is 1, divided by a naught times the Wronskian, which is y1, right? Let's see here. In other words, y1 is equal to the exponential of the integral of minus a1 over a naught dx. In other words, the variation parameters formula reduces the integrating factor method in the n equals 1 case. So I don't know. I don't always tell this to people, but you guys seem friendly, so I told you. And here's how the S formula is reduced to the thing we derived by sort of hand-to-hand combat today by n equals 2. Here's an actual example over here. Oh, I did this one for you guys. Here's the secant example. This is another second order example, which probably would be, well, here's one where the Wronskian works out to e to the 2x. It's kind of interesting. So I solved this problem, y prime prime minus 2y prime plus y equal to f. So you get fundamental solution set e to the x and x e to the x. So when you calculate the Wronskian, you end up with e to the 2x. And here's what the formula 10 gives you. And I'm just doing it for an arbitrary function just to illustrate that you can write down this is an integral solution. This is how this differential equation responds to an arbitrary force in terms of integrals. So there's a use for that kind of thing. If you then plug in specific choices, like if I put in particular f equals to e to the x sine x, then you can do these integrals and you get that particular general solution. I'm sorry, that general solution. I have to be careful. Particular has all of a sudden been given a technical meaning in this course, so I have to be wary of using it. So I try to use specific, where I would sometimes say particular in other courses. Mathematicians are awful this way. You know there's a technical meaning to the word simple? It's true. Here's the awful one. Third order, y prime 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 plus y prime equals to x log x. So here are your fundamental solution set, 1, cosine and sine. The Wronskian is reasonably not too bad. It ends up being almost the same as the one we worked today, right? So the determinant of this 3 by 3, you can just do an expansion on the first column. That gives you 1 times the determinant of that, which gives you this. And then so then to calculate the sub-Wronskians, these things. These are not the sub-Wronskians. These are plus or minus the sub-Wronskians. But anyway, so I replace the reason this x ln x is going here is because that's the forcing function, right? And so we get x ln x from the first one, we get this from the second one, we get that from the third one, and then put it together. So this is like a homogeneous solution, right? Oh, sorry. So V1, I have that one. And it's division by the Wronskian, right? This is Cramer's rule. But the Wronskian here is 1. So, and this are not elementary. Okay, so you really can't do much better unless you're going to go to like a power series solution or whatever. And so there it is. These are tiring. Do I have one more? Oh, no, I don't. Well, that is fortunate. Anyway, I'm not going to assign you guys a third order variation of parameters. I just want you to know that there's a formula out there. You can solve them. You just don't want to. People should pay you money to solve these. They shouldn't be part of your course. Now, second order, that we'll do all day long. No problem, okay? But third order, I want to tell you about, but I don't want to test you on, if that's okay. I hope you won't complain I've taught you something not on the test. No? Okay. It doesn't have to be? No? It does? No? Okay. All right, you can cut it off. Thanks, guys.